But yeah, what were we doing last time? We finished talking about Euclid's Elements, right? And you know, it's this text from 2,200 years ago, absolutely foundational to not just geometry, but really mathematics itself. And it was honestly, it was way ahead of its time. And it's the text everybody used for geometry for the next 2,000 years. But in the 1800s or around about then, people started to realize there's problems here, right? Axiomatic systems, they need undefined terms. You can't define everything. And Euclid just didn't have enough axioms. He didn't axiomatize all of the things that he was assuming were true. I'll give you a very quick example of this. This is the very first theorem, Theorem 1. Can't write. Nope. There we go. Theorem 1 from the Elements. On any line segment, there exists an equilateral triangle. Sort of a constructibility proof if you want. If you took Geometry 1 with me last semester, on any line segment you can construct an equilateral triangle is how I'm thinking of this. And I won't write down the details of the proof, we'll just sketch a really quick picture because the picture sort of gives us everything we need. But suppose I have a line segment. Here's A, B, so I'll label the points on the end. How do I get an equilateral triangle? Well, again, this should be sort of immediate to you if you took Geometry 1 last semester. I'm going to construct it by one of our axioms says what? Says that we can always construct circles, right? Go back to Euclid's postulates, I think it's number 3 or 4. I think it's 3. Says if I have a line segment, I can construct a circle using one of the ends as my center and the line segment as a radius. So that's how terrible is that circle? Not the worst. I can construct a circle like that, and I can construct a circle centered at A as well. So how do I get my equilateral triangle? Well, look at the point where these two circles intersect. There's actually 2 of them, but I'll just choose one. And Euclid's postulate number 1 says what? Says on any 2 points there's a line, right? So now I have A and C, I can construct this line. I have B and C, I can construct this line. And here's my equilateral triangle. Why is it equilateral? Well, because CB, AB, and AC are all radii of the same length. Alright, so postulate 3 said we can construct circles. Postulate 1 said if I have 2 points, there's a line between them. Yet I claim there's a problem with this proof. Where is the problem? The problem is this point C. And nowhere in Euclid's axioms does he ever really say anything about the existence of points. And even though he's sort of imagining, to him this is very obvious, it's this assumption he makes that there's just this infinite number of points everywhere in the plane, nowhere does he ever postulate or axiomatize the fact that if I have 2 circles intersecting, there must be a point where they intersect. Right? As we've been looking at our finite geometries, we know we have lines that don't have an infinite number of continuous points sort of spread out across the lines. So there's nothing to say that there's all these points everywhere on the circle. Of course, that's how he envisions geometry, but it's something that you need to axiomatize. So the problem is that C need not exist. Well, let me not say C need not exist, but there doesn't need to be a point at C. Of course, these two circles intersect. Okay, we'll phrase it like this. But he just doesn't axiomatize that there's always a point of intersection between two circles, right? So two circles need not intersect at a point according to Euclid's axioms, postulates. So he doesn't have enough axioms, and there's other problems. He relies a lot on drawings in his proofs, lots of diagrams that are sometimes misleading, sometimes not even accurate. But again, I think this is where we'll stop ripping on him. Again, it's 2,000 years ago. It's for its time, it's an amazing piece of work. So let's get back to this fifth postulate. Right, you'll recall we had this fifth postulate that said if I have two lines that intersect a third line and the sum of the angles on one side is less than 180 degrees, then these two lines must, if you extend them far enough, they must intersect eventually. Right, that was Euclid's fifth postulate. It's this sort of strange one. More has been written about it than anything else in all of mathematics, and this is where I want to return to. So the fifth postulate. This is usually called Euclid's parallel postulate. Even though it says nothing about parallel lines. Not directly, anyway. And this is because we know that parallel lines are really what this is getting at. It's equivalent to statements about parallel lines. And it's how modern day geometry is done, thinking about parallel lines. But anyway, and this is because it implies the following consequences. So one is the stuff about parallel lines. So through a given point, only one line can be drawn that is parallel to a given line. So this strangely phrased postulate about three lines intersecting eventually if you extend them far enough is equivalent to this way we've been phrasing things so far in this class. I have a given point, a given line. Through this point, there's exactly one line parallel to L. And I'm saying it implies, but it's actually, it's equivalent, so the implication goes both ways. So because they're actually equivalent statements, this is why we usually phrase or call this thing postulate 5 that doesn't directly say anything about parallel lines. We know it's equivalent to this, so we call it the Euclid's parallel postulate. But it also implies a whole bunch of other results that I want to get into. So 2, it implies that parallel lines are everywhere equidistant. And again, this shouldn't come as a surprise to you, right? And we're used to working in Euclidean geometry. If I have two parallel lines, the distance between the lines is never changing, right? But we'll see that in Euclidean, or in hyperbolic geometry, for example, we can have parallel lines that look like this. And I'm drawing them curvilinear because in hyperbolic geometry, your lines really are these curvilinear things. And sort of the distance between these lines, they're parallel because they never intersect, is actually changing. So this parallel postulate sort of gives us results like this, the fact that parallel lines are everywhere equidistant. 3, there exist two triangles that are similar, but not congruent. So again, a unique feature of Euclidean geometry, remember similar triangles have the same shape but not necessarily the same size. So there's two similar triangles, but they're not congruent, right? Because the side lengths are not the same. And that's a unique feature of Euclidean geometry. It actually is a result of this parallel postulate, the fact that similar but not congruent triangles exist. What else? Every triangle can be circumscribed. What does that mean? Well, again, this is just a result that through any 3 points, there's a circle. So every triangle can be circumscribed inside of a circle. Not a surprising result because it's Euclidean geometry, but it is in fact a feature of Euclidean geometry. It's a result of this parallel postulate. 5. This is a really big one. Number 5 is huge. I'm going to put a star on it because it's super important. The sum of the measures of the interior angles of a triangle, in fact, let me say of all triangles, is what? 180 degrees. How do you get that? Well, it's a direct result. It's equivalent. It goes both ways again. It's equivalent to this parallel postulate.
What's that fourth word? Sorry.
The sum of the measures.
Okay.
No, it's written badly. I think it's the fifth word. 5, 6, 7. This is cool. Rectangles exist. Yes, I did. And again, this is, I mean, of course rectangles exist. There's a rectangle, right? 4 90-degree angles. But the fact that rectangles exist is somewhat surprisingly, it's a direct result of Euclid's parallel postulate. So what does this mean? This means if I don't have Euclid's parallel postulate, if we change that to something else, which is what we do in other geometries, hyperbolic geometry, spherical geometry, and so on, these non-Euclidean geometries, if we drop that, then none of these things are true. And that's strange, right? How can we even imagine a world where these things aren't true, where you don't have similar triangles, right? If you're similar, you must be congruent. Or triangles can't be circumscribed, or rectangles don't even exist. Or how about this one? Measures of interior angles of a triangle is suddenly not 180 degrees. This is why people were so resistant to this stuff for so long, is because you get these results that just, they seem so strange. And yet, they're all consistent with the axioms you start with. So, what do I want to say? So people spent a long time trying to prove Euclid's parallel postulate, trying to prove it wasn't independent, trying to prove that it's a theorem of the other 4 axioms that Euclid starts with. And they realized that Euclid's parallel postulate was equivalent to lots of these different things. Maybe we can prove one of these things is true instead and we'll be fine. But you can't do any of that either. So consider, I think it's number 5. Let's consider a proof of 5. So here's my theorem. The sum of the measures of the interior angles, measure of the interior angles of a triangle, is 180 degrees. So again, I don't want to write down a whole bunch of words here, so we'll just sort of sketch a proof. It's actually a really sleek proof though. So here's a triangle. Any arbitrary triangle. I want to show that those interior angles add up to 180. So here's what I'm going to do. I'm going to come up with this clever idea of, let's cut it. Let's cut it into 2 triangles. And we'll label these interior angles. We'll call this interior angle A, B, C, D, E, and F. And I'll say, let's let X be the sum of the measures of the interior angles of a triangle. So now I want to let X, I want to show that X is equal to 180, right? That's what we're trying to do. Well, I have 3 triangles here, so let's come up with some equations. How about this first triangle? A, B, F, A plus B plus F must be X. Right? I also know that C plus D plus E must be X. And And what does that mean? If I add them all together, a plus b plus c plus d plus e plus f, that's equal to 2x, right? So a plus b plus c plus d plus e plus f, that's equal to 2x. Now, what are those two equal together? B plus C, what's that equal to? These are complementary angles, right? They form a straight line, so they must sum to 180. So now B plus C is 180. B plus C is 180 degrees. And the remaining stuff, A plus D plus E plus F, A plus D plus E plus F, well, these are the sums of the measures of the interior angles of the whole big triangle, right? So the rest of that is also equal to x. And A plus D plus E plus F is equal to x. So combining these, what do I have? Let's substitute. Substituting, subbing in, we have x plus 180 is equal to 2x. And therefore, 180 is equal to x, as we want it. Pretty clever, pretty sleek proof, using the fact that supplementary angles add up to 180, and using 3 different triangles in this picture. Where's the problem? Right, so what I'm saying here is this doesn't look like I've used the parallel postulate at all. And yet I'm claiming that the parallel postulate directly implies this result. So somewhere it's being used. This doesn't seem to rely on the parallel postulate. But it does. It's hidden in a very subtle way, and I'm not going to prove that this next thing I'm going to tell you relies on the parallel postulate. But I've made a very subtle claim here that's more than what I started out wanting to prove. Or a little bit weaker than what I wanted to prove. It's this line. I'm assuming here that all triangles have the same measure. Right? So I start off with this assumption that all triangles have the same measure, and then we prove that that measure must be 180. But as we'll see, if we get rid of the parallel postulate, then not only do triangles not have angle sums of 180, but different triangles have different interior angle measures, which again is a strange result. But we did. We did use it. We assumed all triangles have the same angle measure. And again, it turns out that this is equivalent to the parallel postulate. And maybe that's not as hard hitting as I'd like it to be, because I'm just asking you to trust me that that's equivalent to the parallel postulate, but it is. So anyway, where do I want to go from So we're finally wrapping up sort of all of this history, this introduction to axiomatic systems, some of the history behind Euclid's elements. The next several sections get into some of the history behind Euclidean geometry that I don't want to talk about. But I'll give you a quick recap of what all these sections say. So what was that? That was 2.2. Now we've got 2.3 to 2.6. This is titled Modern Euclidean Geometries. Next class we'll talk a bit more about 2.7, which is some of the history behind people starting to delve into these non-Euclidean geometries. And then we'll finally get to chapter 3 where we prove results again, where it starts to feel like a proof-based course. But modern Euclidean geometries. And 2.3, is it 2.3? Yeah, it's probably 2.3. I think it's 2.4. But anyway, 2.3, very short section. I think in the text it's just a couple of pages long. We've got Playfair's postulate. So this is coming back to, I think, 1795. And it's attributed to him because he's one of the first people that sort of states Euclid's parallel postulate, postulate 5, states it in a nice way. So Playfair's postulate says the following. It says essentially the parallel postulate we're used to writing. So for every line L and every point P not on L, there exists a unique line M that contains P and is parallel to L. Okay, so like I said, almost immediately, within a few hundred years of Euclid's elements being produced, people start questioning this fifth postulate. People start questioning this fifth postulate, and one, they recognize it's strange, right? Euclid himself recognized it was strange. The way he had phrased it was odd. And almost immediately, people started asking, why, in fact, they criticized him for it. They criticized, why did Euclid include this as a postulate or as an axiom when we can just prove it as a theorem from his other axioms? We don't need it, it's not independent. And of course people spent a long time trying to prove it as a theorem, they couldn't, but they started coming up with logically equivalent forms. And this is of course the form we go with these days. This is Playfair. So Playfair comes along and says, shows that this is logically equivalent to Euclid's fifth postulate. It's the form we've been going with for a while now, but I just want to sort of give this guy a name. So it was this guy Playfair. I believe this is all he's known for in mathematics. But he comes along and he gives us the modern day form. And throughout this course, when I talk about Euclid's parallel postulate, I don't mean Euclid's fifth postulate, right? Not the weird form. When I talk about Euclid's parallel postulate, I mean Playfair. Okay, so this is the form we're going with. 2.3, 2.4. Now we're getting into modern Euclidean geometries, like I said. So first up in 2.4, we've got Hilbert. Hilbert's axioms. So I believe he published these in 1899. This is the same David Hilbert as I mentioned before. Remember, he had these 23 problems that he posed. Most of them are resolved now. One of them was the completeness stuff, the Gödel's incompleteness theorems. So Hilbert comes along, and he's the first person to finally put modern Euclidean geometry on a solid axiomatic foundation. The problem is, again, it's much more complicated than what Euclid started with. No, not 5 axioms. He's got 23, I believe. Actually, no, sorry. He's got 16. So this feels it's kind of nice because when you read them, it feels like the type of stuff Euclid was doing. It feels like you're reading his axioms. He just has a lot more because you need them. So he's got 16 axioms total to actually build up this nice, not necessarily complete, but this nice axiomatic system where you have all the axioms you need, where you're not just assuming things are true without stating them. So this is the first time, again, more than 2,000 years after Euclid publishes his Elements, that someone finally fixes the mistakes. 2.5 then gets into another axiomatic system that still builds up Euclidean geometry, and it's done, I think, 33 years later. It's 1932. A guy named Birkhoff. Pretty famous mathematician. I want to say I remember his name from physics too, from electronics. Is there Birkhoff's theorems or something with parallel? Anyway, Birkhoff, so this is 1932. He does the same thing. He comes up with an axiomatic system for Euclidean geometry, and his is totally different. It doesn't feel like Euclid's axioms at all. It's very, very sleek, but he has undefined terms like distance and distance angles, so this is very different. Very different from Euclid or Hilbert's axioms. And he does this, in fact, he does this in a very sleek way. He has less axioms than Euclid had. He has only 4. So he has only 4, and it's very sleek. So it's 4 axioms. But his axioms are pretty long. There's a lot loaded into each axiom, and they're talking about, distance and angles and stuff in every single axiom. So it's very sleek, but I don't think it's particularly popular because of this. So now we get into 2.6, which is sort of going to underlie our axiomatic system, or a set that we use in this class. I won't really refer to these axioms very often. There's a whole bunch of them. But in comes SMSG. This is an organization that I believe SMSG stands for School Mathematics Study Group, or something like that. But the history here is basically, this is now 1950s, I think late 1950s. Of course, the Cold War is solidly underway at this point, late 1950s. And America starts to get this impression that the Soviets are just much better than us at mathematics and science, right? So Congress comes up with a solution, Congress forms the NSF. So Soviets are at least presumed to be better at math and tech in the 1950s. So Congress establishes the NSF. And their main goal is to fund a bunch of programs to improve math and science education. Right? How are you going to get better at math and tech? Well, educate better. So funds a bunch of improvements to math and science education. And one thing that came out of this is the creation of some sort of so-called new math, better ways of teaching mathematics, which I guess is still happening all the time. But so the SMSG comes out and they develop new math. And most of what they came up with, I don't know the history here, I don't even know what the hell they came up with, but most of this didn't survive or was never implemented. But one thing that did survive was their axiomatic set for Euclidean geometry. So, most never implemented. Most never implemented, but their axiom set for Euclidean geometry survived. And it's a lot like David Hilbert. So when you read these axioms, it feels like Euclidean's postulates. It feels like Hilbert's postulates. So it's like Hilbert. But instead of having 16 axioms, like Hilbert had, they have, I thought it was 23, it's 22. Like Hilbert, but 22 axioms. What does this mean? If Hilbert has only 16 and we have 22, that means, assuming that Hilbert was sort of a minimal set, that means we have too many axioms here. In other words, we can't be independent. Some of these have to be non-independent results, but that's okay. And this is why they developed this way. It's because we don't necessarily have independent axioms, but it makes it easier to teach this stuff. And this is what they wanted to do. They were trying to make this easier to teach. So 22 axioms, not all independent, but easier to teach slash start with. So I suppose that's one thing I should have said about Hilbert's axioms, if you want to go back and sort of write a quick note, is one of the big problems with his axiomatic set. I suppose this isn't a problem, but to start with it, you have to prove some very basic, some very obvious results from his axioms that are hard to do, they're painful to do. They need to be done, but if you're just trying to teach this stuff, it's a little messy to have to start there. So SMSG sort of takes some of those basic results and they just axiomatize them. And then you no longer have to prove them from the others. You don't have an independent set of axioms anymore. But that's okay. That's not their goal, right? So at some point, in one class, I think I will give you these axioms. We can skip a few of them because they're based on sort of based on 2- and 3-dimensional things, or 3-dimensional things that we don't have to care about. But I think there's still about 15 of these axioms that we will have to care about. So probably sometime next week I'll give you their axiomatic set because it's what we're going to go with. But for now that should suffice. And then we have 2.7. So we start to get into these non-Euclidean geometries, the history behind this. A guy named Sakiri comes along. There's all sorts of big name mathematicians. But I think we'll do that next time. So like I said, I was gonna sort of record seats, but sit where you wanna sit next time, I'll record it and we'll end early today.